Good morning. I hope you're doing well. I'm doing fairly well. It was a frustrating week at some times, many times, but progress has been made. We're headed in the right direction, no doubt. But yeah, this optimization stuff is certainly not my forte, and I feel like I'm just kind of like wandering around in an abyss. But we're getting there, and yeah, I'm keen to show you what I've come up with. So let's get on with it. So yes, we are working towards an optimum geometry of the robot. So yes, the first thing that there were a couple things that I went through this week, and the order of them it was like, I don't know, it was a bit of like a back and forth between like collecting data, running some form of optimization, looking through the rest of my code, and then I don't know, having a play around with the robot and like, yeah, doing lots of different things. So there's a lot of back and forth. But yeah, the first thing that I think is the most important was actually, hi Lawless from Poland. Nice. Yeah, the first thing that I realized was actually as a result of something that someone said a couple of weeks ago. They mentioned that as I was kind of jiggling the robot around, that there might be a bit of slop in some of the joints, and that this slop could be causing some of the issues with not being able to position the robot where I want it to be. And I commented at the time that there's actually not that much slop in the robot anymore since I replaced the joints that attach the platform to all of the legs. That got rid of a huge amount of the slop. That was definitely the biggest offender at the beginning. But yeah, reflecting back after that live stream and in subsequent weeks, I've realized that while that is true, that there is very little slop now compared to what there was before, there is still some. And there's one spot in particular where the slop was particularly bad, which was the quick release joints that I had between the leg and the base. And to show you what these were, this is what they were like before. Well, actually what they currently are still now. So on each of the legs, yeah, I'll explain why I decided to do this before in a sec, but for now, these legs are all attached with, like, this is the magnetic joint that attaches the leg to the base, and then to attach the, like, female part of that magnetic joint, I've got a little holder thing in here, and then that attaches into the actual base with just a single screw, which the hole is around here. So through here, through there, a bolt goes in, and then, yeah, attaches this guy down into the base. And yeah, so the reason why I did this initially was because I was, a little while ago, probably almost a year ago now probably, maybe even more, the geometry of the robot was changing quite a lot. So I was relatively frequently changing where the legs were positioned and how they were attached, and then also changing the geometry of the platform itself. And because I was going through all of these changes, it was really annoying to have to continuously screw and unscrew like a whole bunch of different spots. And I wanted these legs to be able to come in and out much faster so that I could more easily make those changes. But of course, there's been so many instances where previously I was designing something for, like, specifically for modularity, but then by the time, like, as soon as I got the modular design done, I stopped making changes, which is so frustrating. Yeah, it's kind of like, I kind of wish that I did the modular design at the very beginning, and then I could handle, like, actually benefit from that modularity, and then at the end, once I settle on a design, then I ideally would have come up with like a rock solid final idea. I guess that's just the way it goes though. So yes, since I made these joints, I haven't done anything with them. And perhaps unsurprisingly, because there's only a single bolt attaching these guys into the bottom piece, there is a non-zero amount of slop in there. And of course, because these are all 3D printed parts, in here I've had to add a little bit of tolerance. So particularly about like wobbling about this axis through here, there's a little bit of jiggle in there. Yes, that's no good. So I am now replacing them with these guys. And it's essentially the exact same thing, except this is all one solid piece now. So if we have a look at the cross section, we bolt straight through the red piece, the printed part, into the female magnet bit, and then that goes straight onto the base. And this should be a lot more solid. I haven't changed these over yet though, because my printer is slow and it takes a bloody long time to print these all off. So I've already got 5 of them, and the 6th one is printing right now. I apologize if you can hear it. I was trying to get it done before the stream started, but again, my printer is very slow. So yeah, later today I'll replace these over, and we will hopefully be completely, maybe not completely, but more rid of slop than we were before. As far as I can tell, these are the biggest offenders now, but they are still like way less than the platform joints were before. So we're definitely, in that regard, definitely progress, but yeah, I'm not actually too sure how big of an effect this slop is going to have on the testing that I'm doing right now, because all the testing that I'm doing involves moving the platform to a given spot, pausing there for a bit, waiting until we are solid, like until we're certain that the platform's not moving anymore, and then continuing to the next pose. So I'm not sure how much slop would actually affect these results, but it definitely would affect the dynamic results. But yeah, I think that's definitely a step in the right direction. And I will continue to monitor all of the different joints around the robot as well to see if I can find other locations of slop. There are 1 or 2 where there's like a tiny bit, but they're going to be kind of annoying to change. For reference, those ones, the next biggest offender that I can see right now is in some of these joints here that attach this swivel node up to this guy. So this one that spins here, that for some of them, I think that this bolt is not tensioned optimally. So there's a tiny bit of give in like where this washer is. Yeah, so I could probably go around and tension some of those, but they're all done up with Loctite, and I don't really want to touch those. So I think if I encounter issues with slop later on, I might go further down that pathway. But to be honest, I think making the changes to the original platform joints and then also to these leg joints, I think is significantly better than it was before. All right, cool. So yeah, no more slop. It's very nice. I've also, when I was kind of scurrying around through my code base, I realized that there's one big assumption that I've been making, which could, maybe, we'll see, have fairly large implications for how the robot moves around. And this thing is that my assumption was that the leg spools, which I'll show what they are in a sec, are 22 millimeters in diameter. And so what these are is in all of the legs, we have this spool down here, which the string wraps around. And let me hide this so you can see it a bit better. And you can see the string path here. Although I haven't gone through and updated this yet. So this, you may, if you're paying close attention, you may realize, actually no, I did update it. Yeah, no, this is correct. Yeah, so this spool is nominally, we can see, I guess I'm blocking it, but it's nominally 22 millimeters in diameter, according to the CAD. However, the effective radius that the string actually follows is going to be slightly larger than 22 millimeters, assuming that the spool actually is printed to be exactly 22 millimeters, which I'm assuming. But yeah, the effective radius is actually going to be a little bit larger because the string itself has some size, right? Like these strings are nominally 0.8 millimeters, so it's not very much, but they still do have some size. You also may be wondering if the string ever bunches up on itself to like increase the diameter by wrapping over itself. And as far as I've seen, that never happens. The strings, there is enough width in here to fit the entire stroke length of the legs so that the string never coils over itself, as far as I've seen. And I've watched them pretty carefully and I've never seen that happen, so I'm fairly confident that that's okay. But in any event, the string itself does have some thickness. And originally I didn't really pay too much attention to this. I just thought like, yeah, whatever, it's 0.8 millimeters. Like that's nothing. It's not gonna make any difference at all. But after working with the hand mechanism now, which operates on a fairly similar principle, where we have where are we? Over here. I don't have the string. Oh, I do have it. I need to change it to a nice yellow. Actually, I don't know. Black is more correct. But anyway, we've got a spool here that the string wraps around, and it's the same sort of thing. The string wraps around the spool, and that causes the hand to move up and down. Here, I would expect the string thickness to make a bigger difference because the spool diameter is so much smaller. And in our experimentation, John and I have absolutely found that this does make quite a big difference. So if we assume that the spool in this case is 9.75 millimeters in diameter, and then get the hand to move around, that moves the hand in a certain way. But then if we experimentally derive, I guess, what that effective diameter is, the hand moves in a much more controlled, better way. The way that we have done that experimental derivation, if you can call it that, is to basically connect the O drive to the computer so we can read out the O drive's position in revolutions. And then, let's get rid of this, move the hand right down to the very bottom, see what that measurement is, let's call that like 0 revolutions, and then we move the hand all the way up to the top, which we know in the hand's case, that is a known length. We can see in the CAD, like we know exactly how long this linear rail is, which is, as I said last week, that's the only thing that we actually know for sure regarding the platform. But we know how long that linear rail is. So we can say, okay, this distance here is whatever it is, let's say 359 millimeters. And then we look on the O drive, and the O drive says, okay, I've moved 11.2 revolutions, or whatever it is. And then from that, we can divide the revolutions by the number of millimeters, and then we can know for sure what the effective kind of like conversion is between revolutions and millimeters for the hand. And that works very nicely. Like that has allowed us to control this hand much, much more precisely than just assuming that the spool is the diameter that it is, that it's supposed to be. Unfortunately, I can't. What I want to do is that exact same process, but for the legs, because up until now, I've just been assuming that all of the spools are exactly 22 millimeters in diameter, and taking what I've learned from the hand, that's probably not correct. I mean, that's definitely not correct, but it's probably going to lead to some amount of issues with controlling how long the leg actually is. And this is obviously fairly important. Like if we want to move the leg to be 200 millimeters extended, if the mapping between revolutions and millimeters is wrong, then it might actually end up going to 205 millimeters or 195 or somewhere in between. And yeah, that's obviously not good. But yeah, annoyingly, unlike with the hand, where we know exactly how long this linear rail is, and we can use that to be like our number of millimeters traveled, I have no such benchmark, I guess, to go off of with the legs. All of these carbon fiber tubes, these were actually not cut by me. These were cut commercially. I bought these. So I do trust their length fairly accurately. But on the bottom of all the legs, not shown in the CAD, I have a little foam piece, and that is squished to different levels for all the different legs. So I don't know how big that is. And yeah, even then, like when the leg is fully extended, I don't know if this will play very nice. Let's go up, down. When the leg is fully extended, oh, come on. It doesn't really, like, it just contacts these rollers. Like this red part just contacts the rollers, and I don't know exactly where that contact point is actually going to be, especially because these rollers are made of TPU and they kind of flex a little bit. It's all a little bit, I don't know, hazy. So yeah, what I've done here, instead of taking like the full stroke and dividing that by the number of revolutions traveled by the motor, I've done a similar thing, but not over the full stroke. Now, I am all open to suggestions on how to do this better, but the best way that I could find to do this was using my trusty ruler. And what I did here is basically the same thing as what I described with the hand, except instead of going from the very bottom and calling that 0 and then going to the very end and knowing exactly how many millimeters that is, what I did is I've measured how wide my ruler is here. It was 18.2 millimeters. So I moved I took all of the legs one by one. Let's bring this back down. I put my ruler in between, put my ruler in between this surface and this surface, making sure that there was no string or anything in the way. So I put this in sideways. I said, okay, that's 18.2 millimeters. I then read off of the computer how many revolutions the motor was then at. And then I also measured my ruler length this way. And that was 171 point something millimeters. And then I put it in the exact same spot. So I go, one end of the ruler is against this face down here, and the other end is against this face up here. Of course, this time the leg was like, I don't know, up here somewhere. And then I took the number of revolutions that the motor had traveled in that case. And I went around and did this for all the motors, and then from there we could figure out what the exact revolutions per millimeter mapping is, and vice versa. And that kind of worked. It felt okay. It was kind of repeatable. Like I did it more than once on one of the, I did it twice on one of the legs just to kind of check that it was correct. And I was within like 5 decimal places of the same mapping. So it was like 0.0000 something off. I think it was like 2 off. Yeah, so the difference was 14.12096 times 10 to the negative 3 and 14.16007. So it's like, yeah, pretty close, pretty close. I feel pretty okay about that. I would like to be able to use the entire stroke length as well. Like, that would be good, but I can't think of anything that I have in my space that is like the right length for that I can measure to be a certain length, because my calipers only go to like 220 millimeters, I think. So yeah, I'm stuck to doing only like the bottom kind of half of the leg's travel, which is a bit annoying. Interestingly, I guess maybe expectedly, all of the legs actually have very slightly different conversion values. So I don't know exactly why that is. I guess maybe the spools are printed slightly differently. There's another thing that I'm a little bit kind of irked about, which is that these spools, so the way that the string path goes in these legs is it goes, the one that pulls the leg to be longer, goes around the spool as you would expect, up through here, through this carbon fiber tube, and then it goes up over this printed black pulley, and then down, it's not actually in the CAD here, but it attaches to this hole in here, and that pulls the leg up. This spool here is printed, and originally I just kind of assumed that didn't make too much of a difference if that was not perfectly circular, but I have since realized that it does make a difference, and if this is kind of like slightly elliptical, then that will affect how the leg gets pulled up, which is a bit annoying. And yeah, that could be a reason why some of these legs, why all of the legs are slightly different to each other. I don't know exactly the precise reason, but I think there's a couple spots where this difference could be arising. Yeah. So just looking at comments, Stormy says, having a solid reference point is important for calibrating these things. Yes, nice to hear you found a solution that marries a real-world object with the CAD and real-time math. I have a feeling it'll be more variable when the spool is filled versus empty. A slightly non-linear mapping, but hates a start. Yes, I agree. I think it would be great if I could... Yeah, it'd be awesome if I could take like different mappings at different lengths, like move the leg to like a quarter of the way along, and then half, and then 3/4, and then the full length. That'd be great. But unfortunately, I don't know. I can't think of any way to do that with the things that I have on hand. Yeah. Yeah, cool. So, as you may expect, I have gone into the code and I've changed these for all of the legs. And we can see whether this actually makes any difference at all. So up here in the corner, I've got a... I've been doing like a test square pattern where I've realized as I was putting this PowerPoint together that I should change this around, but the way that I've got it right now is that this point is 0, 0, and then we go to 100 millimeters in the X direction, 100 millimeters in X and Y, and then 100 millimeters in Y, and then back to 0. I should really change this so that it goes like, so that 0 is like in the center rather than in one of the corners, so that we kind of do like plus 100 and minus 100 of both X and Y. I should change that, and I'll hopefully do that. I'll try to do that soon. But in any event, this is the before I adjust the calibration. And this looks very reminiscent of the sad face that we saw from last week, where the whole thing is kind of like shifted up. And I suspect if this is going to mimic the sad face that we saw last week, if I did have this data in the negative zone, then the blue line would kind of be like up, shifted forwards and to the left of the yellow line. And for reference here, the yellow line is the commanded positions, and then the blue line is the actual observed measured positions. Also for reference, only the points here are actual data. All of the lines in between are just plot juggler filling in the gaps. So don't focus too much on where the lines are, just the end points. So yeah, this is before adjusting anything. This is assuming that all the legs are 22 millimeters. Oh, sorry, all the spools are 22 millimeters in diameter. And then after adjusting it to make all of the legs the like correct mapping, it's so much closer. Like this already is such a big difference. And of course, it's a little bit hard to see when they're just side by like this. So I overlaid the two results over each other, kind of hackily. I just lowered the opacity of one of them. But you can get the idea. Like the red one is after adjusting the mappings, and the blue one is before. And I'm just realizing that the red is actually might be kind of hard to see. So I'll circle out where the points are. So there's one here, there's one here, one here, and one here. So it's significantly closer than the blue ones, which are like here, 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 and here. So yeah, already that has made such a big difference. I was very, very, very surprised by how big of a difference that made. And to be honest, part of me is kind of like, well, we're significantly closer than we were before, so maybe we can just kind of call it here. But I don't know. We can talk about this again once I go through the rest of the slides. Yeah, so I'm very impressed with this. I was not expecting that to make such a big difference. And again, I'm not even certain that this that these mapping values that I found are actually correct. Like they could be off by a little bit. And as Stormy mentioned, there could be a nonlinear relationship here, where as the string winds up the spool higher and higher, that's going to affect things a little bit. And also the fact that that upper spool might be slightly elliptical, that could affect things differently at different stages of the leg extension. So yeah, all things considered, I was very impressed with this. Very happy. Cool. But yes, as I said, I would like to get this geometry as, I would like to get the virtual geometry as close to the actual geometry as possible. Especially because like this test that we're doing here is only pushing the platform out to 100 millimeters in the most extreme case. Like that's not very far. Especially because the platform can actually go, I think, about 350 millimeters radius away in the furthest position. So this is really not it's not testing the entire workspace by any means. And really, when Jugglebot's juggling, we want to be able to use as much of the workspace as possible. So I don't think we should stop here. I think we should definitely keep going. Despite what I may want to do. So yes, let's talk about the progress that I've made with the optimization itself. After having some water. So first question is, how many variables are there here? How many unknowns do we need to solve for? Well, there are the attachment points of all of the legs, because these attachment points, while I feel pretty good about them, especially these new ones where like this female magnet part is much more solidly mated to the part that actually attaches to the base, there could be some deviation in here. Like maybe this is like a millimeter off to the side from where it should be. I suspect these errors should be pretty small, and yeah, I'll talk about that more in a bit. But they could be a little bit off. So yeah, there's the XYZ position of all of these ball magnets. They could be in a lot of different positions. Yeah, with some level of error. So that's 18 unknowns, XYZ for all of them. We also have the same thing for the platform nodes. And again, I feel like these should be pretty good, because these are like these joints up here, more specifically, I can pull up this sketch. So it's these. Oh no, that's not it. Oh, I don't know where I've got it. But it's basically the center point of like where this, if you imagine like an axis going through here and an axis going through here, it's where those two axes meet. And to be honest, it feels like that should be pretty good. But again, it could be like a millimeter off in any direction. And this is also in the platform frame of reference. So if we were just looking at the platform and we had the origin of the platform, which is kind of like around where my mouse is now, from that point, where are all of these platform nodes? And yeah, again, it feels like they should be pretty good. But we still don't know for sure exactly where they are, so we should consider those as unknowns. X, Y, Z, for all of them, is another 18 unknowns. We also have the fully retracted length of all of the legs. So this is, let's just look at the leg, because the CAD's going to go crazy. So this is the length. Is this not? Lol. Oh, I haven't done it since I've changed this. Let's quickly mate this. No, not sideways. I like that it does that sometimes. All right. Yeah, so that is the length of the leg when it is as retracted as it can possibly be. So if we stop this from moving side to side, it is this length here. Except you've got to remember that I have a little foam piece in here so that when the leg goes through its homing sequence and it rams this down, we don't just have like a super hard impact, and it can kind of be made less abrupt, let's say. Yeah, so I don't know exactly how tall each of those foam pieces are, so that's, yeah, makes it a bit tricky to just assume how long that is. This is one of the variables that I am the least confident in, because all of these legs have slightly differently compressed foam bits, and yeah, so they could be slightly different to each other. So also, just for full clarity, that like fully retracted length is the length from like the center of this magnet up to the center of those two axes that I showed before. So if we have this, like, imagine like that, like the center of the axis that passes through here and the one that passes through that point in there. So that length in there. Yeah, when the leg is fully retracted. And let's unfix this so I don't forget later. All right. These are another 6 unknowns, so each leg could be differently retracted. So that's another 6 unknowns. As I said before, while I am feeling a lot better about this mapping between the leg revolutions and the millimeters traveled by the linear actuators, I'm not 100% sure that that value is correct, because my whole ruler thing, while it felt kind of good, it's not like, it was not super solid. Like it's, yeah, especially to like multiple decimal places. It's not like micron level precise or anything like that. So I'm going to consider these still also unknowns. So that's another 6. So in total, we have 48 unknowns here, which we need to find the optimum values of, so that when we move the platform to a given spot, it actually goes to where we want it to. Which is a lot of unknowns. For reference, I've been doing a lot of study, I guess you could say, in various optimization algorithms this week, and pretty much everyone suggests to start with like super basic problems. Like there's a knapsack problem where you've got like objects that have a value and a weight, and you want to figure out exactly how, like which objects you should pick so that you optimize your values, given that you have like a limit on how much weight you can take. And like, oh, that looks so good. It's like 2 variables. It's like weight and value. Like, oh, nice. But yeah, and I had a bit of a look into those, but I don't know. I have a habit of just kind of like jumping straight into, like, I want to use these things as a tool to solve my problem. Like, I don't really care about becoming an expert in optimization algorithms. I just want to solve this one problem and move on. So yeah, that probably explains some, that will explain some of the approaches that I've been taking that I'll explain in a sec. So then the question is, we've got all these unknowns, but how do we even start with fitting any model to the data that we've collected? And what even is the data? Well, what I've done, actually, sorry, I'll explain what the data is in a sec. But how do we fit the model to, I should have had these in the other order, but how do we fit the model to the data that we've collected, which I'll explain in a sec. The way that I've been handling this is that I've been only considering the measured pose and the measured leg lengths. So for reference, I get the platform to move to a certain spot, like in that square example, I get it to move, I tell it to move 100 millimeters in just the X direction. And then I look at how long all of the legs are when the platform is in that pose. And then because we know that the platform is not actually going to be exactly in that pose, we then look at, or we also consider where the platform actually is. And to get that data, I'm using the motion capture cameras that I've got, and I take the centroid like of that rigid body, and I say that that's where the platform is. So we look at the measured pose from the motion capture cameras and the measured leg lengths, which are reported by the O drives, which is in revolutions as well. We then choose a given robot geometry. Let's say that we start with the geometry that I am assuming is the correct geometry, which is all very, very symmetric, very beautiful. It's like procedurally generated. It's very nice. But as we know, it's probably not correct. But we choose whatever geometry we want to test. We then move the virtual platform to the measured pose. So we say, okay, the platform is, it has a translation of whatever the like XYZ position is, and it has a rotation of whatever the rotation measured is measured to be. And then we calculate with this geometry, with the platform where it is, what are the leg lengths that will put the platform there. And this is using inverse kinematics, which is particularly useful because for parallel mechanisms like Jugglebot, or the platform part of Jugglebot at least, those calculating the inverse kinematics of these robots is fairly straight. Like for a computer, it's very easy. It's just like one line of matrix math, and that's it. And then you can go from any given platform position and rotation into, you can use inverse kinematics to calculate, okay, we have the platform here, the base is here. It will just spit out in one line of matrix math, it will spit out how long all of the legs are that will get the platform into that position. It's so good. And that is opposed, of course, to forward kinematics, where you say, I have all of the legs being this long, where is the platform? That is significantly more difficult with parallel mechanisms. I didn't realize that this could be done this way with inverse kinematics. I was always assuming that I would be taking the measured leg lengths and then using forward kinematics to figure out where the platform should be, and then comparing that forward kinematic solution for where the platform should be against the measured position of where the platform actually is, and then optimizing the geometry that way. But that would be significantly more difficult because this forward kinematics for parallel mechanisms is much more difficult. As far as I'm aware, I've never actually attempted it myself, but from what I can tell, you kind of like need numerical solutions, because otherwise you can get weird like inversions. Like it'll solve so the platform's like in the floor, and in like really, you can get, I think in the worst case, you can get 48 different solutions for a given number. Like if you say the legs are all this long, then I think in the worst case from memory, you can get 48 different solutions of where the platform could be, that would make it a lot more difficult to do what I'm trying to do here. But yeah, because we can use inverse kinematics, it's a lot more straightforward. So we've calculated how long the legs should be for the given geometry that we've got and the platform being in the pose that we measured. We can then compare those calculated leg lengths against the measured leg lengths. If the calculated leg lengths and the measured lengths are exactly the same, then that means we've landed on the geometry that the robot actually has, because that's the only way that all of these things can line up that way. But unfortunately, well, let's just assume that the geometry that we've chosen is not the actual geometry of the real robot. Then we will have some amount of error in here. And we look at that error and we say, okay, given that we have this much error, let's try a new geometry, see how that one goes. And then from there, we've got two samples, and then we can decide how we want to decide how we want to choose new geometries from here. And this is where all of the different optimization algorithms come in, because the very naive approach that I mentioned last week was a brute force method, where I would basically just say, all of these 48 unknowns, I'm going to allow them all to have some amount of error, let's say 1 millimeter in any direction, and I'm going to discretize those into 100 positions. So all of these different unknowns can be in 100 different spots within plus or minus 1 millimeter of where they actually are. Across 48 unknowns is what, 4,800, it'll maybe be more than that if you're kind of combining them all together. I don't want to do math on the fly. But in any event, my naive approach would be to basically just generate a huge list of all of the different geometries and then just go through these one by one. And then go through this exact process that I've described here. And then by the end of that, we take whatever geometry has the smallest error and we say, yep, this is the best geometry that we found. This is probably closer, at least, to the actual geometry. But that would probably take a very, very, very long time to run. And yeah, it's very not optimal. So a big part of what I'm doing this week is trying different optimization algorithms to do that in a bit of a more clever way. So that for example, we test a given geometry and we say, whoa, that error is really, really bad. Like that's worse than the original geometry. Let's change all of these parameters by quite a bit and then see what happens. So we change them all by quite a bit. We try that geometry and see what happens. And then we say, okay, this is a bit closer. And then we can like kind of hone in to that area. So that way we spend a bit less time running calculations for geometries that we can assume are probably pretty bad and focus more on the areas where the geometry seems to be pretty good. And there's a whole bunch of different algorithms to do this sort of thing. There's a lot of different approaches. Anna Catherine says, I've only been loosely following this project, but I'm wishing you the best and I think it's pretty cool. Thank you, Anna. I also think it's pretty cool. And yeah, thank you for your well wishes. It's definitely, these last couple of weeks have definitely been more draining than in the past. I can feel that it's so close. Like it's so frustrating knowing that like I know for a fact that this hardware can do so much, and if I just had like the right ones and zeros, this would be so good. It's so frustrating. But yeah, we're getting there, and I appreciate your kind words. Thank you. Okay, so yes, now let's talk about the actual data that I've got. So I started with just 60 poses, and then I've gone up to 108 poses. And I'll show you what those look like here. Sorry, I didn't really... Come on, there we go. Yes. All right, don't look at that. That's a spoiler. So we've got... Sorry, I just need to find it. No. This guy. All right, so what my poses look like now, I've got this Calibrate Platform Pattern Generator. There's a link for this in the description if you want to check it out yourself. But that allows me to put in different variables like how many radii do I want to test, what those radii are, what angles I want to test, and yeah, various, I mean, you can see the different things up here if the text is not too small. The general idea here is that we basically generate a heap of points, and then I'm telling the code, I basically set what the limit of the angles are. So in this case, I've used 15 degrees, and then it will pick some number of different angles to be at those different positions, and it will just randomly choose an XY, like a pitch and roll angle to be at within that 15 degree limit. It then also checks that, it just does a very quick naive check to make sure that all of these poses, or to make sure that we filter out the poses that are not reachable. And the reason why this is kind of naive is that I'm only looking at the position aspect of it. I'm not looking at the orientation. And yeah, I'll talk about that more in a bit. But we can see down the bottom here that we've got various position extremes. So in this case, we're going between -330 and 330 millimeters in both X and Y. In Z, we're going between 130 and 200 millimeters from the very lowest position of the platform. And in this case, we can reach all 108 poses that we've generated. So this is very, very similar to the actual 108 pose dataset that I've got. And we can see here that this covers pretty much the entire workspace. Like there's definitely some areas that are a bit more sparse than others, but it does a pretty good job of covering as much as it covers a lot of the workspace at least. Keep in mind as well that it's I think it's going to be very uncommon that the Juggabot, that the platform moves into this upper and really lower regions. I feel like the platform will stick within this area where all these poses are most of the time. Yeah. Also for reference, the plot Z-axis here is in the base frame. That's why it's like 700 instead of 130 and 200. Yep. So these are my poses for the 108 pose dataset. The reason why I started with 60 and then I went to 108 is because the 60 pose dataset is a lot smaller. It doesn't cover the entire workspace. The angles are a lot less extreme. And yeah, after I generated that, I realized that it's trying to fit my robot geometry to a dataset that only takes up like a third of the workspace is probably not going to be very optimal, because then as soon as we move outside of that zone that we've calibrated for, those calibration results could be a bit spurious. So yeah, that's why I've gone up again. But it's good because now I can use this 60 pose dataset as kind of like a reference to validate the different results. Also, if you are curious to play around with any of this, all of the code that I've been using here is in a link in the description. So I've got these pose, I've got like the recordings that I took during these calibration routines. And yeah, it's all there so you can do whatever you want with it. Yeah. And yeah, I'll try to remember to talk about that in a sec. Yeah. So both of these data sets as well have the original motion capture origins. And the reason I'm bringing this up is because I think that might make a bit of a difference with how they are fitting the data. So what I mean by the original motion capture origins is, can I bring this guy back? Yep. The platform origin should be it should be here. This, if I can click on it, that point right in the middle there, because that is perfectly coplanar with all of the platform joints. That is where the origin is supposed to be. In the motion capture software, I originally left the origin as this marker here. So that point is actually, what is it? The center distance is 13.3 millimeters above the actual origin. And I'll talk about that in a bit. But so the platform one is off a little bit, and also the base one is off a little bit, because this is the guy. Let me actually change to this one. So this is the robot as it actually is right now. This piece, I am still waiting for it to be made by JLC 3DP, so I don't actually have that yet. Instead, I have the kind of truncated one that's flattened off here, and all of the markers are just attached straight onto this guy. So in that case, the origin is off by 35.8 millimeters minus the radius of the marker, which is 7 millimeters. So it's about 28 millimeters below. Sorry, the actual origin is about 28 millimeters above where the motion capture origin is. Yep. I have been dealing with that by basically telling all of the algorithms that I am using to optimize this robot geometry. I'm saying, hey, I expect all of the base nodes to be offset by 28 millimeters from where the motion capture thinks it is. And similarly for the platform, I'm saying I expect the platform nodes to all be 13 millimeters below where the motion capture says they are. I am not sure if that's, yeah. I'll continue on that line of thought in a bit. But that's what I was doing originally. And that's what those first 60 and 108 calibration pose datasets, that's what was set up in those cases. So I'm just saying that just in case anyone wants to try to optimize this themselves so that you know exactly what those data sets were. And yes, I'm trying several optimization techniques. So we're dealing with least squares, the TRF, and dogbox. These are both like variants of the least squares algorithm. Also doing min TC, which I can't remember what the TC stands for, but yep. Also differential evolution, which seems like a pretty good way to do it. This one has like, you generate like, it'll generate the set of, this is the one that I understand the most, so I'm going to try to explain it a bit. It basically picks a set of those 48 variables, gives it a try, picks another one randomly, gives that a try, and then figures out like how good both of those data sets are. And then there's a variety of ways to combine these, but in whatever way you choose, the end result is that you basically take some of the variables from this guy, some of the variables from this guy, combine them together to make a new like child like variable set, and then try that one. And you can go through kind of iterations of making parent variable sets and then children variable sets. And the idea here is that if you pick only good parents to make children, then you should end up kind of like honing in on the regions where there are like good solutions. That's the idea. And then I've also tried a hybrid solution, which involves differential evolution and least squares, because according to ChatGPT, using differential evolution is a very good way to kind of like survey the entire search space, but then least squares is apparently much better at dealing with very local optimums. So the idea with the hybrid solution is that we can search the entire space broadly, and then once we've kind of arrived at like a good local, like a region where it seems to be pretty good, then we hone in really hard on with least squares, is the idea. And this is the result that we get. So here I've only plotted the 36 unknowns of the base, well actually only really, what would it be, 24 unknowns of like the XY positions of the base attachment points and the platform attachment points. So all of these are also offset in Z a little bit, and I'll show that in a sec. And then we also have the millimeters to revolutions mapping and the minimum retracted lengths of the legs, and those are not displayed here. But we can see that, well, first thing you may notice is that you can't see any of these data points. We can't see anything for the least squares or the min TC. And the reason for that is because they are perfectly coincident with the hybrid results. So all of the, what are they, purple, kind of like plum color, all of those plum X's are also where the least squares and the min TC, they all agree like to like, what is it, like 7 decimal places I've got it printing to, and they are like spot on to 7 decimal places, all of them, which, to be honest, I'm kind of a bit sus about, but whatever. But in any event, these platform ones look so wrong. Like the base ones, like, yeah, okay, I can kind of see if the base is like that far off. Like those kind of make sense, especially the differential evolution results. They look kind of on par with what I would be expecting. Like just a smidgen off where my initial guess is, but not too far off. But then the platform connection points, like those are, I do not believe that the platform nodes are that far away from where I think they are. Like that, especially the differential evolution one. Like what is that? The platform nodes are definitely not basically on top of each other. Like that's not true. And I don't, yeah. So actually, I want to also show the other results here. So actually, one thing first. I kept getting these results as well. I ran this with a whole bunch of different settings, and I've been setting different bounds for how far, like how much error I expect there to be for each of these different variables. And I've played around with these quite a lot, and like enforcing different penalties. So I say like, I expect the leg, let's say the mapping between the millimeters and the revolutions, I expect that to be within like 5% of my measured values. And if the solver finds a value that's like 15% away from what I've calculated, I can give a penalty to that. I can say, hey, that's bad. I don't think that's correct. Like that's a bad result. We should not consider that to be a success, even if the mapping is like ostensibly correct. We should say, no, that's bad because I know it is. So I played around a lot with these different penalties and the different bounds, and I keep getting effectively the same results as this. And I was like, well, maybe it's right. Maybe let's just give it a go and see what happens. And oh my God, I've been so nervous to run these because every single time I've run Jogglebot in like the last year has been using my initial geometry, and I've got like several layers of kind of like safety guards in place to stop the robot from just like destroying itself. And one of them kind of relies on the geometry being the way that it is. And yeah, I was very nervous to try this out the first time. I had my hand very actively poised over the E-stop button just in case it went somewhere wrong. Because yeah, changing this geometry around is a big change of like Jogglebot's kind of like proprioception. So yeah, I wasn't super eager to do this, but I figured like if I keep getting the same results, maybe I should just give it a go. And I did, and I'll show you those results in a sec. But of course I had to pick one of the results here, and I could, like, just looking at these results and what I said before, it looks like the best one. It looks like the best one to pick would be the one where kind of like all of these solutions are in agreement. And like, to be honest, those results, I'm still not a big fan of like this zone over here. Like, why are they like that? But yeah, so my first thought was like, okay, I'll use those. But then once I actually looked at the results a bit closer, I'll show you this here. Bring me back. Let me make this text a bit bigger. So we've got, yeah, let's look at like so actually these are the initial guesses, and you can see all these variables here. Note in particular, the fully retracted lengths are all 640 because these are just, again, procedurally generated. I'm just assuming that they're all the same. And then we've got these conversion factors, and these are from my measured values. The reason why they're different from what I said before is because when I was measuring it before, I had revolutions per millimeter. These are then the reciprocal of that, so millimeters per revolution. And we can see, yeah, they're all slightly different. Some of these two are pretty close, and like the second one and the last one are pretty close, but they're all a little bit different to each other. But just kind of like pay attention to the kind of rough order of magnitude of these. And again, while I'm not certain that these values, especially the retracted lengths, but more particularly the conversion values, I'm not certain that those are correct, but I feel like they're within like 5%. Like, while my measurement technique was a little bit dodgy, it wasn't like 20% dodgy, you know? Yeah, so I'm expecting conversion factors to be around this region. But what we see is from the least squares solution, which again was the nominally better solution, where we had like 4 different solution methods in agreement, and also we didn't have this weird like kookiness with the nodes being basically coincident. Despite that, I really don't think that these solutions are definitely not correct. Like, the retracted lengths are like, okay, maybe we're like 25 millimeters off, maybe. But the conversion factors, they're so far off. Like that, if this was the case, then the legs would be extending, what is this, 75 to 105. That's like 30%, maybe even more, difference between where we're telling the leg to go and where it's actually going. And there's no way it's that far off. So I find this hard to believe. And again, as I said before, the different least squares methods are all in like very suspiciously perfect agreement with each other. It's very weird. I don't like it. It's wigging me out. It's like 105.2569 whatever. 105 it's exactly the same. And the same thing for min TC is the same. Like, the conversion factors, like, no, definitely wrong. But then we get to the differential evolution one. And this is where, like, we see, like, these two nodes are, like, right next to each other. Like, not a fan of that. But the conversion factors are much closer to what I measured. I'm still not a big fan of the fact that all of the retracted lengths are identical. I think that is more likely to be different than the conversion factors. Like, there's no way the fully retracted lengths are all identical, which is something that the other solutions do manage, is that they are all solved a little bit differently. But because the retracted lengths and the conversion factors were closer to what I was expecting, I was like, okay, cool. I'll try the differential evolution solution and just see what happens. I didn't want to push this too hard because, again, I'm very nervous about changing this geometry around and I don't want the robot to destroy itself. But, where are we? Right button. I love it. Why is it not? Oh, because I'm minimized. God. All right. Yeah, I didn't want to destroy itself, so I just got it to do the square from before, and this is the result that we got. So this is from, square after first geometry update, and it's like it's wrong in the other direction. Like, what? Like, maybe I can just kind of like take the average between my assumed geometry and this calculated geometry. Maybe, I don't know, but it's definitely still wrong. Like that's probably as far off as the original like solution that we got before I adjusted the spool spool diameter. So I don't like this. This is definitely not correct. And again, like, this is only pushing the system to 100 millimeters in any of the extremes. And also, just for actually no, I'll show. There's something else I want to show, but I'll show it in a sec. Yeah. So as I expected, that solution is definitely not correct. Like, the fact that these are where they are is a big indicator that something's wrong here. But I don't really know how to improve it. None of these make sense. Everything's a bit whack. So what I did is I said, okay, cool. Maybe the fact that my rigid body origins are not where, like, according to the motion capture, the origins are not actually where they're supposed to be. So let's just record another 108 pose sample. But this time, in the motion capture software, I have offset all of these. I should just keep this here, shouldn't I? In the motion capture software, I've just offset both the base origin, which is the global origin, and also the platform origin, so that like the motion capture origin is actually at the platform origin. Like, in QTM, you can just say, I want this rigid body origin to be positioned so that whatever marker I choose, in this case I've chosen this one, is at these local coordinates. And I've just done that so that the platform origin in the motion capture system is actually where the platform origin is. And that way, rather than setting bounds of when I was doing this before, I was telling the system, I expect the platform origin to be, like, I want to give like a bit of error. So I'm saying, like, I want it to be within, what is it? In fact, it was 13 millimeters below the motion capture origin. So I was telling the system, I was telling all of these optimizers, I expect all of the platform nodes to be between 10 and 16 millimeters below where they're measured to be. And yeah, I was talking with ChatGPT a bit about this, and it was saying that if you have like a systematic offset like this, when you're using these sorts of optimizers, you should really kind of try to separate these things, and rather than trying to fit to this systematic difference or offset, it's ideal if you can like resolve that systematic offset before you feed your data into these optimizers. And that way in the optimizer, I can just say, I expect the error to be within plus or minus 1 millimeter, rather than like plus 10 and plus 16 or something like that. And I was like, okay, cool, maybe that is making a difference. So I recorded another 108 pose sample, which again is in a link in the description. It's called something obvious, I can't remember exactly what it is, but it's like 108 pose after adjusting origins or something like that. Yes, and unfortunately, that didn't make very much of a difference at all. It made very, very little difference. So yeah, not super, I don't know. Yeah, I was hoping for a bit more of an effect there, but yeah, unfortunately not. So what are my next steps? I'm thinking maybe rather than dealing with all 48 of these unknowns at the same time, maybe it could work to handle these individually. So that we say, given this big data set, right now we're only going to deal with the base nodes. So let's fit our data and do this exact same like inverse kinematics process to find the optimum base node positions. And then once we've got those locked in, then do the platform ones. And then once we've got those locked in, we can deal with all of the leg stuff. It's like, maybe that would work, but that feels like it's not... it feels to me like all of this stuff kind of has to be like handled in tandem. It has to all be dealt with together, as far as I can tell. So I'm very skeptical that this sort of like individual approach would work, but I'm thinking like it's maybe an option, and maybe it would help to kind of like avoid weird situations where like all of the legs, the retracted lengths are all identical. Like maybe if we've already handled the base and the platform nodes, and if we're only solving for the legs, like the retracted length, then presumably we're not going to solve for all of those to be the exact same length. Like we would have some variance in there to make sure that the base nodes and platform nodes, so that those assumptions actually fit. Maybe. But yeah, I'm skeptical that would work very well. But we'll see. Another option is to put even tighter bounds on these variables. So I said before that I've been playing around a lot with different bounds and different penalties for these. The whole time I've been really umming and ahhing about like how much error I actually expect there to be in all of these joints. And from memory, the tightest that I've gone is plus or minus 5mm on all of the joints. But I'm thinking now, especially having a look at the CAD and having a look at the actual robot, I have a feeling that the error is going to be less than that for all of these nodes. Like the base nodes, like they are bolted in with 4 screws into the base, and like these parts are like, they're not tiny. So like the error of where this hole is not going to be 5mm. Like no way. Like I can measure with calipers to make sure that it's less than 5mm. And like all of the holes in the base, they were cut out with the CNC machine, and I trust those, and like they match these holes perfectly. So I think that those, as far as I can tell, those are perfectly positioned. So yeah, 5mm in hindsight feels a bit of a large error margin. So I'm thinking that maybe if I tighten these bounds down and apply a really harsh penalty to going outside of those bounds, then maybe we can arrive at a more accurate solution. Maybe. I'll give it a go. And my final thought is to just try the brute force approach. Because something that you may have gathered from all of my discussion about this so far is that I'm far, far from an expert in optimization techniques. Like I really don't know what I'm doing with all of this stuff, but I do know what I'm doing when it comes to brute force. Like I am very comfortable with setting up, like I've done that before. Like that's what I did for finding the best Stewart platform geometry, is just set up a simulation with like, I can't even remember, it was like a couple 100 million test geometries, and I just let it run for like 2 days. And I'm like, I'm not going to be using my computer this weekend, so maybe I can just set that to just brute force run for like 2 or 3 days, and we'll see what we get. I'm very tempted to do that because, like, yeah, there's been a large part of this week has just been like waiting for that routine of like collecting 108 poses. That takes around 10 minutes to run. And like, yeah, I just have to sit here and just wait and make sure that it doesn't, like, I don't know, that nothing goes wrong, which it very rarely does, but like it's just boring. Like I just have to sit here and just, like, I have to be paying attention to it, so I can't really be doing anything else. So I'm just sitting there waiting for that to run. And that had to go a couple times because various things, I say that not many things went wrong, but there was one time where like something that I've mentioned a couple times in the past is that every now and then the O drives tend to just kind of like lose their calibration. I don't know why. I don't know what causes this, but it's just like, it just happens after like a little while. And like, for example, yesterday when I was trying to do one of these runs, it got like 7 minutes through this like 108 pose collection. And I was noticing that like one of the legs kept not reaching its destination when all the other legs did. So like I get it to move to a pose, and I have a report saying like, we're waiting for the platform to arrive at its designated pose. We're waiting in particular for leg number whatever. And it was just the same leg again and again and again until eventually it got an error. It got a spin out error because it had lost its calibration and for some reason forgot how to control the motor, I guess. Yeah. Thankfully, it's pretty easy to resolve that. I can just get the leg to go through its calibration sequence and then it's good again for another couple of weeks, I guess. But yeah, so I had to do a lot of waiting around for that to run. Running these optimizers takes a really long time as well. It's like 20 minutes or so on my computer to like run, especially the differential solvers takes a while. So there's just so much like waiting around. And I'm like, the devil you know is better than the devil you don't. And I don't really know what I'm doing with these optimizers. I'm just kind of like, I don't know, messing around and hoping that something works. So maybe it is worth just like committing to the solution that I'm more comfortable with, but is way, way less efficient. But efficiency doesn't really matter because I'm only doing this. I should only need to do this once. So yeah, that's kind of what I'm thinking. One other thing that is worth mentioning is that, let me go back to here. The original two datasets, so the 60 and the 108 pose datasets, they were both collected before adjusting the leg spool diameter. So like this, I'm fairly sure that these were done before adjusting the spool diameter. So those original two. And yeah, so we can see here the effect that I was describing before. We're like close to the origin. So this is within 200 millimeters. Like this is pretty close. Still pretty far away, but not super far away. Within that 200 millimeter circle, like it's pretty good, to be honest. Like it's actually not that far off, but as we go further out, it gets further and further away. But then the last 108 pose one, after I offset the origins, that was done after I did the 22 millimeter offset thing. But you can see again, it's not great. Yeah, it's fine within like about 200 millimeter radius, but as we go further out, it gets worse and worse. Yep. So yes, progress and also roadblocks, I guess is the summary of this week. Yeah, but we're getting there, and I feel okay about this. Yeah, I'm coming to terms with the fact that it's pretty unlikely that we're going to get the exact optimum geometry that is like perfectly matched to the robot. So I'm kind of coming to terms with the idea that it's unlikely that we're going to be able to get the robot to move to like exactly where we want it to be, especially when we get it to move really far out from the center point. But I'm also kind of leaning into that a little bit. And I'm thinking that even if it doesn't reach exactly where it's supposed to go, I think we can just design the hand mechanism and like the catching process to compensate or to be tolerant of these sorts of errors. And things that will work in this direction are, for example, making the hand a bit bigger and also using these sand-filled balls, because these just plop. They just land and they stop. And so even if the robot is like if we're looking at here, even in some of these cases where it looks to be really far away, like where are we? Like here, for example, at these two spots, that's only, unfortunately, I don't know of any way to like show to like highlight like crosshairs on here. But we can see from the data on the side that like the X position is negative 213 millimeters, and the commanded position is, where are we? 243. So this one is 30 millimeters off. And in the Y direction, it was the measured was 86, and the commanded was 101. So that was 15 millimeters off. So 15 millimeters and 30 millimeters, which sounds like a lot, but also like 3 centimeters is not even the radius of the ball. Like it's pretty close. The radius would be like 3.5 centimeters, but still, it's less than half of it's less than the radius of the ball, which should mean if we make the hand big enough, then even if it lands like over here, it's still going to plop in. So, yeah, maybe I'm just kind of giving myself a bit of a crutch here to lean on, but I don't know, I'm kind of like changing my expectations a little bit to allow for this process to not be perfect. And to be honest, I think that is, the more that I think about this and the more that I work through this, I do think that it's unreasonable to expect that we can perfectly position the robot to exactly where it should be, given the way that the robot is constructed. Like all of these 3D printed parts, that spool that I said on the legs, how it's like, it's printed, like that will mean that the legs will probably not be following a perfectly linear relationship between revolutions and linear distance throughout its entire stroke length. So as we get further away from the center point, when the legs are more extended, it's possible, I would say potentially likely, that the legs are not actually the length that they're supposed to be. And calibrating for that is going to be very, very difficult to do, I think. So it's a bit of a trade-off, as everything is, between spending more and more time on getting this optimization working versus reaching a point where I say, yep, that's good enough, and then returning back to actual juggling stuff, which I'm so keen for. It feels so close. So right now I'm definitely on team continue optimizing. I feel like I haven't finished this. I've still got a lot of unresolved questions, like all of these next steps that I mentioned. Like I want to try these things out. Maybe not if I have time, I'll try the handling unknowns individually. I'm particularly keen for the brute force. I really want to see what that spits out. But yeah, I'm not expecting this to be perfect. Yeah. Which, I mean, that will probably more accurately resemble how humans juggle anyway, because like our proprioception, especially jugglers' proprioception, is like decent, but it's definitely not perfect. Like anyone who's tried juggling 6 balls knows you cannot throw the balls in exactly the same way every single time. Like you're gonna be a little bit off, and so you have to be able to compensate for that, which is something the Jugglebot's going to need to be able to do anyway, especially when it's juggling with another person, or with a person. So, yeah. Setting expectations. So as I said, all of the data that I've collected here is on GitHub, and that includes all of these. Let me move me over so you can see this stuff. That includes all of these topics over here. So I probably should have gotten rid of some of the unnecessary ones. Like I think that the hand, I swear there's more in here than that are actually, than are displaying here. But yeah, there's some data in here that you won't actually need. But importantly, we've got this settled leg lengths, which is once the leg has moved to its position. I probably should have explained this before, but the general workflow for this, and also why we're seeing this kind of like stair stepping, and we saw this last week as well, where there was like stair stepping in the leg positions. The reason for that is because I'm getting the platform to move to its position. We're then waiting to confirm that the platform has arrived, and the way that is determined is in all of the O drives, they have a flag saying like trajectory complete. And we tell all of the legs in trapezoidal trajectory mode with a very naive, just like go here approach. We tell them like go here, and once they've arrived, that trajectory complete flag or trajectory done, whatever it is, that becomes like yes, our trajectory is done. So once all of the legs confirm that their trajectory is done, then we say okay, we've arrived, and then the platform still waits. I've got it set to wait for 2 seconds, and then once that 2 seconds is done, then we take a recording of what are the leg lengths measured by the O drives and what is the pose measured by the cameras. And then we report those variables to these settled leg lengths topic and the settled platform pose topic. So these are like once it's actually arrived. Versus, for example, if we wanted to see the actual like in motion data, we can see like this. So this is what it looked like as it was moving between all of the poses. And you can see it's definitely not following an optimal approach. Like what is going on here? What is this? Why, when you're moving from here to here, oh, my camera's right there. Let's put me down there. Yeah. Why has it decided to like go all the way off to the side and then back again? Bit weird. But yeah, that's why I've taken only the settled data. But yeah, you can play around with all of that. One thing that I think is particularly important to mention, if anyone does want to try their own optimization approach, which I'd love it if people did. Like, I am not expecting myself to be able to get this perfect. Honestly, I'm thinking that my brute force approach is probably going to be the best approach that I'm going to be able to come up with, but that's definitely not going to be perfectly optimal. But yeah, one thing that's worth being aware of is that in some of these poses, despite me doing the naive check that all of these poses are in fact reachable, some of them, especially in the more extreme positions and the more extreme angles, some of them had the legs hitting their limits. And when that happens, the leg just like caps out. It stops. Like, before I send the command to the O drive, I first truncate the position that I'm telling it to go to so that it stays within the limits. So some of the commanded poses were not actually reached. And that's why when I'm doing all this fitting, I'm using the measured pose and I'm completely disregarding the commanded pose, because the commanded pose was not always reached by all of the... Oh, sorry, not all of the commanded poses were actually reached. That data is still here. So if you wanted to have a look at it, let me move me over again. Where is it? Yeah, like the leg lengths topic is before the data is getting truncated. So that will not reflect what the platform is actually trying to do. And also platform pose is as well. I don't know. If you are interested in trying any of this optimization stuff yourself and you have any questions, definitely ask on Zulip. I can give you whatever you want. If you want me to do a particular run with like the platform in a like following certain pose combinations, I'm more than happy to do that. Yeah, I'm very, 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 very open to work with you if you want to try this out yourself. And yeah, I can give more detail on exactly what all of these things are and how they were recorded once I have a bit of time to like sit down and actually think about it and write it out properly. Yep. Yeah, so I guess the TLDR is we're getting there. Improvements are being made. Slop is being removed, which is nice. But definitely still progress needs to be done. But we'll get there. Cool. Again, I forgot to check my calendar before this, but I'm fairly sure I'm not doing anything next Friday. So I will see you then. And yeah, I hope you are well until then. And good luck with everything you're doing. And yeah, I'll see you next week.